Hello class, this is Tuesday, May 19th, 2020, Coronachem day 31 for period 4 for 12U and AP. The homework you had on Friday was to do question number 1434. It involved plotting second order data. So it says for a second order reaction, what quantity when graphed versus time will yield a straight line? B, how do the half-lives of first order and second order reactions differ? So I've got the first half of the question answered here. So you plot 1 over A concentration versus time, and you will get a straight line if it's second order rate data. The intercept will correspond to the rate at, of course, if you go to time 0, because you could theoretically start at a non-zero time, but if it goes to time 0, then 1 over A naught gives you initial concentration. That's the intercept. So it's plotted in the form of y is equal to mx plus b, where the y part is 1 over A, the x part is time, and then the slope ends up being delta y over delta x. Okay? And part B of the same question. Poses the question, how do the half-lives of first order and second order reactions differ? The half-lives of first order reactions are not affected by the concentration of reactant. In second order reactions, they are. And just to remind you, in first order reactions, T to the 1/2, the half-life for the reaction is given by 0.693 over K. Whereas in a second order reaction, T 1/2 is equal to 1 over A naught K. Good. The next subject I want to bring up is something called the transition state. So let's first of all, excuse me, I've been exposed to a lot of dust lately. Let's find out what the transition state is. As the molecules involved in a reaction strain to achieve a new geometry, and arrangement of atoms, some bonds stretch, others break, and new ones form. The point at which a molecule or molecules goes through the point at which a molecule or molecules achieves maximum strain on the way to achieving products is termed the transition state. The transition state is the point of maximum strain, and if you were to plot the transition state versus the reaction coordinate, you would get something like this. You could have the reactants starting here, products are here, perhaps at a lower energy level, and the point at which the molecule goes through the transition state is the point of high energy. And there's another energy that goes from here to there, which is basically like passing over a hill to get to the downhill part where the reaction then proceeds to products. There's an input of energy involved here. This is an endothermic process usually, not always, but it requires an input of energy. And this is called the activation energy. The energy between the reactants and products is the heat of, it could be the heat of formation or various other things depending what you're looking at. There are four things that affect the ease with which a set of molecules or a molecule can achieve the transition state. And let us look at what those four factors are. Four factors affect the rate of a chemical reaction. First is temperature. Higher temperature means more frequent collisions, and you remember we covered similar factors for rates of reaction, but now we're focusing on the transition state. So we're a bit more specific than what we talked about at the beginning, although they're going to have similar, obviously similar effects, because higher temperature will increase the number of productive collisions, but it also increases the number of collisions resulting in the transition state. So we're just focusing on the nitty-gritty details of what happens when a chemical reaction takes place. So higher temperature gives higher increased collisions and increases productive collisions, which means collisions with enough energy. Because sometimes a collision can happen, but it happens with insufficient energy and it doesn't lead to reaction. Then collisions themselves. So an increased number of collisions increases the number of possible reactions. Temperature is not the only way to increase the number of collisions. It is also possible by increasing the number of molecules per unit area. If you increase the concentration of the reactants, or if you increase the pressure on a gas, the gases are closer together, the molecules are closer together, they're more likely to bump into each other. So increasing the number of collisions. Increased collisions. Increasing concentration and pressure increases the number of collisions as well. The third factor is the orientation of the molecules when they collide. Molecules must collide in the appropriate alignment to proceed to reaction. Some collisions do not produce a reaction because the appropriate parts of the molecules do not meet. Say if the reactive faces of the molecules are face to face, if there's such a thing as face to face. But molecules do have a geometry. The back side of a molecule is going to have a different geometry than the front side of a molecule. So if two molecules have to collide like this to react, but instead they collide like that, you're not necessarily going to get a reaction, or you might get a different reaction. So this is what we're talking about when we talk about collision orientation. In complex molecules like proteins, it is of paramount importance. If the molecule is not properly oriented when it collides with the part of the enzyme that it's going to react with, it won't work. So that's why the pH of your biochemistry has to be regulated so meticulously by your body. The enzymes have a specific three-dimensional shape, and that three-dimensional shape can change ever so subtly, but just enough to prevent the molecule or the enzyme from working. So orientation plays a big role in ensuring that a reaction goes to completion. So much so that there's a whole industry. Medications a lot of times work on the premise of this factor being altered just enough to create different properties for molecules. You can have medications that block a certain enzyme, or maybe make the enzyme work faster, or you have enzymes that you have substances that imitate a certain building block in the biochemistry of a bacterium, for instance. But then when the bacterium incorporates the medication into its cell wall, it paralyzes, it destroys the cell. It either destroys the cell by making it too weak, or it jams the enzyme that causes a particular thing to be made by the bacterium. So there are many approaches in biochemistry to achieving one's ends. Anyway, orientation. Molecules must collide in the appropriate alignment to proceed to reaction. Some collisions do not produce a reaction because the appropriate parts of the molecule are not aligned. And the last thing is the activation energy. Activation energy. For a reaction to occur, colliding molecules must possess enough energy to stretch and break bonds in order to form new ones. The difference between the energy of the starting molecules and the highest energy along the reaction coordinate is called the activation energy. I drew you a little diagram. So it's the energy difference between the transition state and the reactants. One good example of an activation energy being important in the design of a molecule is the activation energy for explosives. Some explosives have a very low activation energy and they're extremely dangerous because they're easy to detonate. Those type of explosives are usually used as detonators. They're the little part of the bullet. If you see a bullet, the way it's designed, you have a casing that usually necks down, and then they put the bullet in the casing. This is the part that flies out over here. This part is full of powder, and at the back here usually they have a little button that gets hit by the firing pin of the gun. That little button contains an explosive that is very sensitive to being deformed. It's shock sensitive. So if you hit it, just make a dent in the little primer at the back, it causes a small flash, a tiny explosion, and it detonates all the rest of the powder, and then the bullet comes out. So obviously you don't want to make explosives out of the same material that you would make detonators out of, because they would be extremely unsafe. Usually what you do is you make an explosive that has a high activation energy that is very hard to make explode, but once it finally does explode, it releases a whole bunch of energy, but it's nice and safe. So if you dropped it, it wouldn't just blow up. Or you could even hit it with a hammer, it wouldn't blow up. Although, don't go and test that theory out. But you would use a whole bunch of the hard to explode explosive, and then you would put an explosive, a detonator that has a low activation energy so that you can set off the major charge. And that's how explosives manufacture is oriented around. I mean, it's not only about explosive power, it's also about safety. Okay, the transition state is the highest energy arrangement of atoms along the reaction coordinate. I should give you a definition for that too. I'll write that down. So the transition state. The highest energy arrangement of atoms along the reaction coordinate. By reaction coordinate, I mean if you could take a very high-speed film of what happens at the molecular level, you would see the molecule transitioning from reactant to product through whatever mechanism it goes through. It's something that happens in a split seconds. Reactions happen on the order of femtoseconds. So on the order of 10 to the minus 15, if I'm not mistaken. So nano is 10 to the minus 9. Pico is 10 to the minus 12, femto is 10 to the minus 15. So it's on the order of 10 to the minus 15 seconds for reactions. It's not something you can easily take a picture of. So they've put a mathematical formula to this. It's called F, where F stands for the fraction of molecules with the energy greater than the activation energy, and it equals E raised to the power of the activation energy over RT. So let me write that down for you. F is equal to fraction of molecules with energy greater than or equal to the activation energy. And R equals 8.314, it's the gas constant, joules per Kelvin mole. And T is the temperature, the absolute temperature in kelvins. So it is found that at room temperature, only a very small population of molecules have enough kinetic energy to react. But a 10 degree Celsius temperature increase causes a 3.7-fold increase in reaction rate for a reaction with about 100 kilojoules per mole of activation energy. Now, because reactions can speed up with an increase of temperature, a guy by the name of Svante Arrhenius came up with a formula which you could then use to plot a straight line using data that plots a ln of the rate constant for a reaction versus the reciprocal of the temperature. So let me erase that and make room for the Arrhenius equation. So the Arrhenius factor the Arrhenius equation and its development. We can fit it all in. What are we doing for time? Okay. So the Arrhenius equation incorporates all the aforementioned factors, meaning F, so Arrhenius came up with this. K is equal to A times F, where A is the orientation factor. And also K can be put down to A times e to the negative EA over RT. And again, AR is equal to 8.314 joules per Kelvin mole. T is temperature in Kelvin, and F is the frequency factor, or a measure of how many collisions you're getting at a given temperature. Now, if you plot ln of K for any given reaction at a particular temperature, you're going to see that it's equal to, first of all, ln of K is equal to EA over RT plus ln of A. And you can plot this in the form of y is equal to mx plus b, where this is the y part and x part is 1 over t. So, a graph of ln K versus 1 over t will yield a straight line. This is on, I believe it's on page 598 of the textbook. Let me just, yeah, 96, 97, 98. So you'll get a straight line if you plot ln of K versus 1 over t. Obviously, the K's are obtained at different reactions. The K will change if you change the temperature. Sorry, same reaction, different temperatures. Think of the rate constant of electron production in a car battery. What do we all know about car batteries? They work great in the summertime, not so great in the wintertime. So a cold battery, it's because the reactions have all slowed down. It can't generate electrons as quickly because the electrochemical cells just don't react as quickly when the atoms are moving more slowly at the lower temperature. A little trick you can do to avoid a tow truck if you ever get stuck: if you have access to hot water, you can pour it on your car battery, and if you warm up the car battery enough, it might give you just enough power to start the car, provided there is a charge in the battery. If the battery's dead before it got cold, it'll still be dead after you warm it up. But if the battery was charged before it got cold, you can, I've used the trick myself. It has worked. I didn't have a charger once. I was up in the country. I poured boiling water on my car battery. I'm not sure that's such a good idea either, but you know, what was I gonna do? Call a tow truck? I would have, you know, I would have spent the cost of a battery anyway. So it worked. The car started. So you can, warming up some reactions will generate more rapid unfolding of the reaction. And in the case of an electrochemical cell, like a car battery, it might give you enough current to start your car. So let me show you what you're going to do for homework. You're going to do I'll show you how to set it up so that you don't get stuck. But that's going to be your homework. Practice example, page 599. We don't have much time left. Tomorrow I'm going to review the test we just did. Some people didn't hand it in. I don't know what to tell you. I'm gonna post the results. So some of you need to wake up a little bit. Probably you're not watching, so this message is wasted. But you need to take your own education seriously. You're at the age where you're old enough to decide what you want to do with your lives. There shouldn't be any adults standing on your shoulders telling you what to do when you're 18. If that's happening, you need to grow up. Okay, folks? I don't want to be harsh with you, but that's the reality of life. At that age, you have to start thinking for yourselves. You shouldn't be waiting for people to tell you what to do. But on page 599, practice example, you're going to set it up this way. This is how I did it to solve it. I made a chart, because whenever you want to make a graph, it's important to make a table of values that you're then going to decide which ones to plot. Okay, so I had the temperature. I converted the temperature into Kelvin. Then I had the rate constant as the question listed it. Then I took the ln of each value, and then I took the reciprocal of the temperature in Kelvin. So it's in units of Kelvin to the -1. That's what you're going to put on your data table. That's what it's going to look like. Okay? And I think they give you this part and they give you this part. All the rest is derived. And then you're going to plot 1 over ln of, no, not 1 over. It's going to be ln of the k values versus 1 over t. Okay? And you're going to get a line that slopes downward. And the slope of that line m is equal to negative EA over R. Okay, so that will tell you how to get the answer. And to get the slope, obviously, it's like rise over run. Here's your delta y, here's your delta x. All right? So try that tonight. See if you get an answer, and then tomorrow I'll share with you what I got. I make no guarantees about the accuracy of my own answer, but at least we'll get a result. Okay? And I'll see you tomorrow. Bye-bye.